Danièle Roudil, who's going to talk to us about nuclear site integrated characterisation for radioactive waste minimisation. Thank you.
Thank you, Mr. Chairman, and good morning, ladies and gentlemen. I'm going to be talking about waste-laid characterization and sampling methodology and their development in the frame of the Insider project. The co-authors of this presentation are the work package leader of the project, coming from GRC, from NPL, from SCK, UPV, and CE. My presentation will be divided in 4 main parts. We begin by some elements of context to position the project, its objective and organization. I will present, of course, a methodology supported by the project and its implementation. I will move on to the midterm report status, and I will give you, in complement, some feature of the preliminary results obtained by the first benchmarking in the project, and then I will conclude by some perspective at this stage of the project. Some element of context, as it was yesterday explained, we are at the beginning of a big wave of nuclear reactors and facility shutdown, leading to main technical, societal, environmental and economic challenges because of the high number of work sites to be dismantled, and the methodology, associated methodology to be implemented, because of the huge amount of radioactive waste to be produced. Regarding our disposal, our present disposal capacity, and also because of the wide variety of contaminated raw materials to be processed in this operation. An international consensus already exists concerning the importance of the characterization steps and the contribution to scenario definition, to cost estimation, to waste production and characterization. But these operations are costly and time-consuming, and some improvement should be necessary. To lower the duration of this operation, of course, and also for a better understanding of the characterizations in order to refine the modeling and the cartography of the sites. Last but not least, for waste, an efficient waste management leading to a real minimization of the volumes through different potential routes, the reliability of the data it's a key objective. And this is also an issue that should be addressed by the characterization methodology. Let's move on to the Insider project. Insider is the acronym for Improved Nuclear Site Characterization for Waste Minimization in D&D Operation under Constrained Environment. Sorry, it's very long. Insider is a Euratom European project launched in June 2017 for 4 years. It gathers 18 partners from 10 different countries, and it is supported also by an end-user group with 11 more new company, nuclear company, and this group is now shared by IAEA. The Insider will aim at developing new or improved integrated characterization methodology or strategy for nuclear decommissioning and dismantling operation with constrained environments we will address the issue of limited amount of available data while limiting the variability and the sensitivity to outliers. The project aims also at validating through 3 use case study, namely nuclear power plants, post-accidental light remediation, and nuclear facility decommissioning. The project is based on 6 technical work packages represented here in the form of a flower. The sampling strategy is at the heart of the project. It relies on measurements, techniques and methods, analytical methods that will be selected by the work package 4 and work package 5. Work package 5 will be mainly involved in the on-site measurements for the validation of the methodology. And the work package 6 is specialized in performance assessment and budget uncertainty of the determination for all the steps of the methodology. The work package 2 in the core of the organization will provide the other work packages with requirements, actual practices and needs, and it will define and organize the validation on the real cases. The work package 7 is devoted to dissemination and exploitation, and it manages the outcome of the project, namely the communication, but also the knowledge management, the contribution to learning initiatives, and pre-standardization of the methodology and the guidelines. If we want to validate on this 3 case study, we have to apply the methodology on real work sites under decommissioning. These work sites were offered by the 3 partners of the project. Concerning the back end of fuel cycle or research facility, it will be represented by by a liquid effluent tank storage at the GRC Ispra site. The reactor will be the BR3 reactor at the Mole site offered by ICK, and the post-accidental land remediation will be represented by contaminated soil from a CA site. How to implement this methodology in real work sites and how to assess its performance. We can here we could consider 3 main areas: the sampling strategy, and the analytical method, measurement techniques, their performance, and their coupling to the sampling strategy here, and the work site configuration. At the beginning of the project, they were fed by the requirements, the practices, different review and state-of-the-art in terms of analytical method, measurement available, techniques available, and this review and state-of-the-art, some of them will be published. Sampling and analytical measurements and techniques have defined their own methodology. The sampling strategy will provide sampling plan for each of the use cases, defining the condition of the on-site measurement, and of course some complementary analysis in lab in order to produce a cartography. With the sample collection, we will take benefit of interlaboratory comparison tool to organize a first intercomparison in analytical lab on real samples, and we will organize also an on-site measurement comparison on specific identified points located in the sites. To refine all these exercises, and thanks to reference materials, matrix reference materials fabricated during the project, we will organize also an inter-laboratory comparison for analytical lab on matrix certified reference material in order to assess, to have a best assessment of the uncertainty of the analytical method to be used in the first, the previous interlaboratory comparison on real samples. And all this performance, all this uncertainty will be injected in the statistical data processing in order to improve the cartography and have a better and improve also the sensitivity to, of this cartography. This is, we are at the midterm of the project, and this implementation are in progress at the moment, and the interlaboratory comparisons are also organized, and the samples will be sent to the laboratories in the next months. Now, let's turn on to the midterm report status and focusing on the recent development already available for the next step of the project and for other use. The sampling strategy first. General strategy gathering all available data has been defined and is the object of a technical report. It is developed in a waste-led approach devoted to the front end of the decommissioning. Most of the strategy, of the sampling strategy, existing sampling strategy as devoted to the back end of the decommissioning. But it's important to act on the upstream of the decommissioning and to act on the front end and to have sampling strategy also for the front end of the decommissioning. The main focus of this work package is a statistical data analysis associated to sampling design. You have here the picture of the global methodology and the Venn diagram highlighting all the statistical approach, of course with a focus on statistical approach devoted to small data sets here. And this part of this work is devoted to guide the end user to select the appropriate statistical approach for data analysis and its associated sampling design. And we have now a user-friendly web interface available on the website of the project, and that will be used to define the sampling design in the use case. And as you see, the end user is helped to define if it is in presence of a mono or multivariate data analysis, to identify spatial structures, spatial trends, and the needs for robust methods. Other important development concern analytical developments with two main developments. First, the reference material fabrication and certification. The first one is NIVI concrete reference materials based on real samples, inactive real samples doped with barium, cobalt, and europium. And the second reference material is an effluent solution, simulating the effluent solution of the effluent tank of GRCA SPRA, doped with most of the radionuclized identified in this table. These reference materials are ready, and they will be certified and sent in the next month, in June or July, to the lab for the inter-laboratory comparisons. The second development is a liquid-liquid microextraction microsystem used for the purification of difficult-to-measure radionuclides, the iron-55, prior to its analysis. In fact, it implements a new analytical method developed by CE Setama, based on ethyl acetate in the organic phase in order to replace the harmful chloroform, which is no more REACH compatible, and it was used in the past analytical methods, and maintaining the use of capron in aqueous phase in order to form a complex with iron. It's an reactive transfer of iron produced in this single or two-stage extraction chip. The most important is to maintain the interface by monitoring the flow rate in the microchip. We have some measurement of the extraction yields, and these yields could be improved also by monitoring the flow rate. This work was conducted in the framework of a postdoctoral study in the framework and of the project, and this result will be are submitted for publication. I will conclude this rapid report status by some new elements and nuances of the performance assessment. Performance assessment is needed to confirm the ability of the different techniques and methods, to assess the uncertainty of these analytical methods, and to establish a complete uncertainty budget at the end of the project and at the last part of the project. All these assessments are based on inter-laboratory comparison exercises, on reference samples for in-lab destructive or non-destructive analysis method comparisons, and on real samples, either directly on samples on-site for on-site measurements, and on collected samples for in-lab comparisons. And in fact, we will use the analysis of variance approach that allow to identify the different components of variance, inter or intra samples homogeneity, of course, the component of variance of the detection for each measurement or analytical method used by the laboratory, and also the inter-analytical methods variance component. It's the same for in situ measurement, but without subsampling, of course, because it's direct on-site and non-destructive measurements. And you have also the different variance components in order to evaluate the different component of the uncertainty. Of course, to organize this kind of exercise, you have to specify all the requirements, the number of measurements of repetition to the labs, to have an efficient data processing at the end of the intercomparison. Now, a few pictures of the first benchmarking organized past year on the BR3 reactor. It concerns the reactor pool of the reactor, here in red, after removing the metallic liner here on the right. And you have here a picture of one of the teams during the on-site measurements campaign. In the center, you have the building of the BR3 reactor. So we have to have on-site measurement on activated concrete, and we have here a concrete example of the application of the methodology. Here you have a standard sampling strategy, but we wanted to test and to prove the interest and the applicability of the small data sets by lowering the number of available data. If we consider the inter-team comparison, we can define, we were able to define 3 different points with 3 very different levels of radioactive activity. And thanks to the measurement, with 5 measurements with detector in the fixed position, 5 measurements after replacing the detector, different detector to source distance, and with the 3 measurement points, we are able now to have an evaluation of the detector positioning uncertainty, the detector location uncertainty, and the activity or concentration level uncertainty. And this is the first result presented, and these preliminary results were presented 2 weeks ago during the midterm workshop of the project. In the near future, by the end of this year, we will have the result of the inter-laboratory comparisons. The laboratory will receive 2, I'm finished, I will conclude, 2 samples, the reference materials and the real samples. A first inter-laboratory comparison will allow to assess the analytical method's performance, namely the uncertainties, taking into account the unhomogeneity of the reference sample that will be determined during the certification process. And this uncertainty will be used to analyze the results of the comparison on the real samples, because in the reality, the samples are not homogeneous, and it's not possible to have homogeneity in the reality. And we have to correct all the results to assess a best estimate of the measurement value and its uncertainty to be injected in the cartography in order to improve the modeling of the site. We will have a similar approach in September, beginning in September, October, on the liquid effluent tank storage at the GRC, with a lot of radionuclides presented in the tank, and with similar measurement on site, and then samples sent to the laboratory. Now it's time to conclude. This methodology is based on sampling coupled with characterization approaches devoted to small data sets, small amount of available data, but based on a knowledge of the performance of the analytical method and the measurements. It proposes innovative methodological studies based on a multidisciplinary network in the project and contribute to DNDK activities such as matrix reference material, intercomparison on real samples, analytical innovation, in particular for the measurement of difficult to measure radionuclides, integrated approach for site characterization, and also we have a database to capitalize on experimental results. The methodological guides will constitute one of the main operational output of the project and will be open for standardization, thanks to the links established with the ISO Standardization Commission. It will contribute also to a European Learning Initiative and the Länder Initiative in particular, and it will give some input data to other European initiatives such as the CHAIR project and the Metro Decom project. At this stage, we can also imagine or propose a further extension of the methodology to historic waste or, for example, graphite in the graphite reactors. And perhaps also an entry point to digital tools and potential contribution to data management in artificial intelligence approaches. So thank you for your attention. And you have here different possibility to follow the result of the project.
Thank you, Danièle.